Hi. So in this example, we're going to put a few of the probability rules together. So I really like this one, and it really just kind of shows you the depth and the challenge, how challenging these probability problems can get. Okay, so let's go ahead and start. Suppose G-Pod manufactures 100 of their new phones. G-Phone. Because G-Phone is new to the cell phone market, there is an estimated 15 G-Phones that are defected for the 100 manufactured. OG, the creator of G-Phone, decides to test 3 out of the 100 phones. What is the probability of at least one G-Phone is defective? So here's what's happening. G-Pod manufactures 100. And it's known that about 15 of the 100 are defected. So OG decides to have the assistant go down and grab 3 phones. And when they grab 3 phones, he's going to randomly select one of them and see if they're defective and see if at least one of them is defective. So let's write down again on our appendix here some of the information, and let's gather the information. What are some things that kind of come out at you? You're right, 15 phones of the 100 are defected. We're going to test 3 phones out, and the probability of at least one. So those all 3 should have kind of come out at you, because the probability of at least one tells you which formula you're going to use. Okay, so the first thing is the probability of at least one is equal to 1 minus the probability of none. Okay, and then let's list the rest. So we do know that we have 100 phones total, and 15 out of the 100 are defective. Okay, which is what? Right, 15%, or we could say 0.15, 15%, right? And we're going to say that if 15 are defective out of the 100, how many are not defective, right? This would imply that 85 out of 100 are not defective, right? Which means about 0.85 or 85%. Okay, and we are selecting 3 phones. Okay, now that we have all information, let's go ahead and build out the calculations. So the first thing I'm going to do is the probability of at least one, right, is defective. And one what? One of the 3, right, are going to be defective. Now let's think about it. If the assistant is running down to the factory and grabbing 3 phones, is the assistant taking one phone, running back up to OG, giving it to him, taking it from him, running back down, 90 floors, and grabbing a second phone, running up? No, right? What happens when OG tells his assistant, go grab me 3 phones? The assistant is going to go down and just take 3 phones. So do you think as the assistant is grabbing the phones, there's with replacement or without replacement? And if you said without replacement, you're correct, right? Because they're going to take a phone, and there's going to be less phones in the box, less defective, less non-defective, right? And you grab a second one, that changes the probability. Now there's only 98 phones left when you grab that 3rd phone, right? So these would also be, when you select the 3 phones, these are also going to be dependent events. So we know that somehow when I build my calculation, that I'm going to have to use the multiplication rule for dependent events, and also I'm using the at least one formula. Okay, so now I think we're ready. So now the probability of at least one is defective is 1 minus the probability that none are defective. And so this would mean that 1 minus the probability of none being defective. Well, the assistant's selecting 3 phones. So that would mean that the first phone that the assistant selects is not defective. And the second phone is also not defective. And the third phone is also not defective. Well, this is equal to 1 minus the probability of the first phone not defective, and which is times the probability of that second phone not defective, and which is multiplication, the probability that the third phone is not defective. Okay, I think we're ready, right? So we have 1 minus, I'm going to put like brackets here, the probability that that first phone is not defective. Well, how many in the box are not defective, right? Well, we said that 85 out of 100 aren't defective. So when he goes in, there's 100 phones in the box. 85 he can pick that are not defective. So that would be 85 out of 100. Times, now let's talk about the second one. Well, how many phones left in the box? That's right, 99. How many phones left that are not defective in the box? Well, there was 85 to begin with. I already took one. I have 84 in there out of 99. Times that third one, and now you can see the pattern. There's 83 left out of 98. Okay, and so when you do this, I encourage you to do this in the calculator. And we could just do 85 divided by 100 times 84 divided by 99 times 83 divided by 98, and then do 1 minus this answer, which would be second negative, which is answer. So 1 minus this answer gives us 0.3892, which is 38.92%. Okay, and if you wanted a fraction, we could go to math, go to frac, and it may not give us a fraction, but notice that this time it did, and so that's great. So we could also say this is 899 out of 2310. So it just depends how they're asking for the answer. In this case, with this type of application, like with cell phones, I definitely think it's going to be asked for a percentage. I think OG would want to know the percentage. The moment you start talking about formulas and stuff, OG might get a little upset, you know what I mean? So I would just say, okay, if we randomly select 3 phones, so this could go even further, right? So if I sell 3 phones, right, making revenue. So if OG sells 3 phones, there is about almost a 40% chance that one of those will be defective. And if those phones are under warranty, that consumer is gonna come back and ask for a replacement, which is a cost to the company. And so a lot of cell phone companies do this. Apple, iPhones especially, Androids especially, they already know when they produce a certain million number of phones that a certain percentage of those phones will be defective. They already calculate the cost of those defective phones, and then in that they incorporate a price for the phone. So it's very, very technical, very mathematical. Even though it appears it's not, it really is. And sometimes the defect rate is so low for some phones and some cell phone companies that's why they can offer a BOGO on phones. So because it's not going to take that much cost out of them to just replace one that's defective. Okay, fun, right? Okay, so now the last one is addition rule. And addition rule is always nice because it's usually only one event happening, and we're just going to see whether there's an overlap. Okay, so now we can go ahead and talk about the addition rule, where recall the addition rule is with the word or, and we talk about disjoint events. Okay, so if they are if two events are disjoint, then we just add the two individual probabilities together, right? But what happens when there is an overlap of outcomes? Remember the queen and the hearts and the queen of hearts, and we did a Venn diagram? Well, what happens when we have an overlap? So this is going to be our general addition rule, and essentially we can always use this rule for any cases, whether they're disjoint or not disjoint. So again, the probability you might recognize as A or B is equal to the probability of the sum of each event occurring minus the intersection. Because if you have an overlap here between these two probabilities, you're going to double dip, right? You're taking that queen of hearts and adding it to a queen of hearts, and therefore you have now two queen of hearts. Well, you got to take away one of them, right? And so that's what the subtraction is for. Okay, so now let's go ahead and recall that example with Bucky and Satchel, right? Satchel draws a card, he puts it back in the deck. Find the probability for Satchel drawing a queen or a spade. So the event A is drawing a queen, and event B is to draw a spade. So the probability of Bucky drawing a queen or a spade is equal to the probability of Satchel drawing a queen plus the probability of Satchel drawing a spade minus the probability that Satchel draws a queen and a spade at the same time. And so if I wrote this up here, so this would be a queen, a spade. So this is just drawing the queen. The second probability would be just drawing the spade, and this would be the queen of spades. Okay, so let's go ahead and think about that. Well, queens, there are 4 queens in a deck, right? We did this, so it's 4 out of 52. Plus the spades, that's a suit, so that would be 13 out of 52. Minus the queen of spades. And how many queen of spades are there in a deck, right? There is only one, so that would be, let's take out the double dipping, because here I took the queen of spades, right? Because there's 4 queens, so I took it. Here in the spades, one of these cards is a queen, right? So I took that one. So now I counted 2 queens of spades. So let me take away one of them. And that's where that minus comes from. And so we have 4 plus 13 is 17 minus 1 is 16 out of 52. Okay, so if we wanted to just reduce it, we could. It would be 4 13ths. And if we put it in the calculator, we could just approximate it as 0.3077, or in other words, 30.77%. And then I just want to put a note here. So essentially what you're doing is just subtracting or taking away the intersection, right? Or in other words, you're taking away the double dipping.